All right, great. I'm actually recording now. Anyways, so I've been watching the feedback as we go, and there's been a lot of people who really like the code examples and really want to see the things in action. But I think we had to lay some of the groundwork first. But for these last couple days, it's going to be a lot of us walking through notebooks. These are largely notebooks that I've stole from the IBM Quantum tutorials, and largely I've just went through and tried to simplify. They do a lot of large blocks of text. I've tried to turn that into bullet points. I delete some of their advanced examples. And so that's what we're going to do here for the last couple of days. We're going to walk through code and try to um, just kind of see what's going on there. I'll be providing these notebooks and notebooks with more in-depth applications will be available on IBM Quantum. There's a lot of examples there. And of course, as always, please feel free to reach out with any questions. We're going to have a pretty good turnout for the hackathon. Myself and the rest of the hackathon team are working through processing all the submissions and getting them ready, and we're pretty excited. We'll have more information about that in days to come. So we're going to talk about QAOA. This is the Quantum Approximate Optimization Algorithm. QAOA is a hybrid algorithm. We use this algorithm where we use quantum to try to do the hard math part, and then we use classical optimization methods, whether that's a simple SciPy solver that's minimizing it, or whether we can even include it with a broader machine learning pipeline. This example focuses on the max cut problem. It's kind of the simplest problem we can represent QAOA with. However, you can apply QAOA to any type of large combinatorial space. What happens here is that anytime that we have a huge number of possibilities that we're trying to apply and try to understand, how to select the best one based on penalties and rewards, we can apply QAOA. So this has applications to finance, to task scheduling, to routing, to a huge number of options. All kinds of classic problems from combinatorics, things like the knapsack problem, which is a basic problem that says, assume that you have a knapsack or a backpack, as Americans would say, that can hold 10 pounds. And you have assorted in front of you a selection of goods that weigh different weights and have different values. And trying to determine what combination of the items to put in there is a factorial problem. If you have 100 items to choose from, that's 100 factorial combinations. And then you have the trying to understand which one of those combinations that will fit in your backpack have the highest value. Now, that's an abstract way of looking at that, but the same thing's done, for example, in finance all the time. A portfolio has, let's say, $10,000 to invest. It can select, let's just say, even from the S&P 500. And so there's 500 factorial just combinations of stocks to pick even before we get into trying to select how much of each one. So these combinatorial optimization problems are present all around us, and QAOA provides us a way to try to solve these problems. So the basic idea of the max cut problem, all right, involves partitioning the graph's nodes into two sets, all right, and you're trying to maximize the number of edges that cross between two sets of the cut. So this can be thought of as combinations of things. Each edge is a combination of two nodes. This can be expanded to various other problems, but for now, we're just trying to cut the most number of edges while partitioning the graph into only two nodes. So this means that each edge can be crossed a maximum of once, and there's other constraints that are there, but for this little 5-node graph, it's relatively simple to do it by eye, but you don't have to get a very large graph before trying to calculate this maximum cut becomes intractable. So here we have our requirements. We're using matplotlib for visualization. RustWorkX is a NetworkX instantiation that uses Rust as a backend. That way it's faster. And so NumPy, we're using SciPy to optimize. We're using sparse Pauli op from Qiskit Quantum Information. And since we're using sparse Pauli op, we can assume that we're going to be using an estimator. That is, that we're going to be getting a singular scalar value out the other side. We don't have to manually encode our ansats. I could talk about how we set up this portion of this quantum circuit, but this is abstracted away from us. We use our preset pass manager to deploy to real hardware, our runtime service, that way we can sign in. And this estimator, that makes sense given the sparse Pauli op, that we're going to use an estimator where we get a single scalar value. We also have a sampler because there are sampler instantiations. Okay, so we can represent this function. This problem is a function, but what we're doing is our x is a binary vector representing graph nodes, and we're trying to sort them into components 0 or 1. We're just putting our nodes into two groups on whether or not they're included in one partition or another. Then we need to define an edge function. So for each edge between nodes I and j, all right, we can define our edge function as the value of x plus the value of node I plus the value of node j minus 2xi times xj. Okay, so we're trying to maximize the number of edges of cut. Now, in typical optimization, we're minimizing. So all we do is invert this. We take this times -1 to make it a minimization function. So we take 2 times xij minus xi minus xj. Okay, but let's go and get into it. We're going to build our graph. We're saying that we have 5 nodes. All right, we're going to add our nodes to our graph. And we're going to define the edges in our graph, and they all have equal weights. So, an edge from node 0 to node 1 with weight 1, from 0 to node 2 with weight 1, and so on and so forth. Okay, and so we have a graph that looks like this. So our first step is that we need to map our classical inputs to a quantum problem. With any quantum circuit, your first step is always going to be that encoding step, that we need to find a way to represent our classical information that we have into our quantum circuit. Okay? Now, here's a new term, is to a QAOA. QAOA stands for quadratic unconstrained binary optimization. Okay, a lot of times people think that Q is for quantum, but it's actually quadratic. This has existed for a long time as a formulation of these problems, but it's just intractable at large scales on classical computing. So we're going to represent our function that we had up here of this 2xij minus xi minus xj into our matrix, this QAOA matrix, which way we will encode into our quantum circuit. That Hamiltonian is just a state of the quantum circuit. Okay, and then we'll add to that a parameterized quantum circuit. All that means is that we're going to have some parameter, let's say theta, that we will minimize, that we will adjust with our optimizer, whether that's a deep neural network or whether that's more classical methods. It could be an optimizer like Atom or others, where we will try to minimize the value of the output from this by adjusting these parameters. So this QAOA has these two parts. The cost operator, which is this matrix that we're making from the terms of our graph, and then that parameterized circuit where we are trying to minimize the output from that circuit by adjusting that parameter. So we're going to learn what values of those rotations that we apply will minimize this energy function. So to change the notation to our QAOA, all right, what we're going to do is we're going to rewrite this optimization problem in linear algebra terms. Most of the things in quantum computing are written in linear algebra terms. So we're going to take a vector x times a matrix Q times a vector x. This will give us a scalar value at the end, a single output. All right. X is this binary variable vector that is whether each node in the graph is included in which set. So, it'll be either 0 or 1 depending on whether it's in set 0 or set 1. Okay? We can expand this out from our matrix multiplication, that this is what this is going to be. Okay? But this is just this term here, a vector x times a matrix q times a vector x. All right? So to reformulate this as the Hamiltonian, all right, we have this matrix that is our z terms, that is our sparse Pauli operator that we're using with our estimator, plus a bias. All right, this is your cost function Hamiltonian, and we're going to work through it. Please don't worry, but what we're trying to do, once again, is represent the ground state that minimizes that cost function, such that we maximize the number of edges we cut in our graph while partitioning the nodes into 2 sets. Okay, and so what the basic workflow of this will be is that we'll run a value through our quantum circuit, and then we will adjust our parameters to try to get lower and lower energy functions that through our representation of this graph in that QAOA matrix will go to lower energies and thus maximize the number of edges we cut with our objective function. All right. So the way this will output these things is that we're going to have our cost Hamiltonian being our QAOA matrix times a z gate on qubit I and qubit j. So this is what this code looks like. I make an empty list. Then for each edge in my edge list, okay, I append a ZZ term with a weight of 1, because we set all the weights to 1. So this, what we end up here is a Z term where each node is in this list. We have 5 nodes, and there's an edge between node 0 and 1, there's an edge between node 0 and 2, there's an edge between node 0 and 5, and so on and so forth. And all of these have a coefficient of 1. So you might have noticed that I said this is a edge between nodes 0 and 1. Please remember, in Qiskit, we always use Little Endian ordering. So this will be represented as qubit 0. Okay, so to start off, we start in the 0 state, as we do with most quantum circuits, and then we place all the qubits in an equal superposition. We apply a Hadamard gate to every qubit. This lets us represent all possible combinations of splitting these graph nodes into 2 components. Okay, because it has 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 1, etc., etc. So this represents the all possible states of the system. All right, and then we're going to apply unitaries with these angles that we're going to learn to encode our features, gamma and beta, for each node in our graph. Okay, so what we're going to end up here with is we apply our qubits into superposition, and then we're going to repeat applying these gamma rotation layers and these beta rotation layers, gamma, beta, where we have our cost Hamiltonian and then our mixer Hamiltonian. All right, and this is what the simplified circuit is, that we have our QA circuit, we have the parameters of gamma and beta, that our minimizer function optimizes. So step 2 here is to optimize the problem for hardware execution. And just like we spoke about yesterday with how important it is to use smart implementations of our circuit, that way we can minimize the depth of our circuit. So to do this, I specify my Qiskit runtime service, and I just pick the least busy backend. Okay, and I'm using a just generic Heron backend. And then I'm using optimization level 3. Optimization level 3 here means that I want my circuit as optimized as much as the transpiler can handle. Okay, and so with my circuit that I've created here, all right, remember that we had 3 layers here, so it's a pretty long circuit. Okay, but by those repeated layers, it allows us to better learn our parameters to minimize this function. Okay, first things, we have to initialize our parameters, and we're just initializing them, our gamma as pi and our beta as pi over 2. These are just kind of generic, picked at random. Okay, this is a little bit of description between single job versus batch versus session. That's more on how you interact with the quantum hardware. We can go into that in another time. And so now we are going to run our circuit. Okay, we apply the layout of our instruction set architecture, the actual quantum computer that we're using. We define our primitive unified block that has these 3 things. It has our quantum circuit, as well as our parameters, and we use an estimator to run that. With estimator, we're going to get an expectation value, a singular scalar value, and then our cost is just going to be that singular value. Okay? And so, what we'll do, this is further things that you can do to optimize your circuit. These are all error mitigation steps. And this is something that we're getting more into in this afternoon session. This is going to be part of our afternoon session. But I'm saying here that I want to use dynamical decoupling. And what that does is it tries to prevent crosstalk between qubits to where the operation I do on one qubit doesn't affect the other. Pauli twirling is a way to minimize that gate over rotation where, hey, I told the gate to rotate by pi over 2, but it actually rotated by pi over 2.1. Okay, and then from SciPy, I'm using the minimize function. This is just going to optimize my parameters. Okay, so I have my cost function estimator, which is just the output of my quantum circuit. I have my initial parameters that I'm doing for that initial gamma and beta we defined of pi and pi over 2. Okay, for the args, you know, you have your candidate circuit, your cost Hamiltonian, your estimator that get passed to that cost function estimator. Then method here is QAOA. Now, if you're not familiar with quantum computing yet, you may not have seen QAOA. What QAOA is a gradient-free optimizer. On quantum circuits, you have to increase the number of measurements that you do by quite a lot for gradient methods to work well. You have to, because you'll get these noisy outputs, and so oftentimes, especially for quantum circuits that we're running for fewer shots, where we're checking the output fewer times, we will use a gradient-free optimizer like QAOA. And then we have our tolerance. So, you know, what we've done here is we've encoded the graph features with our cost Hamiltonian. Okay, our mixer Hamiltonian provides entanglement between those, but it's an ansatz, which means it has trainable parameters, this gamma and beta, that we are passing to our minimizer, and we're using this SciPy minimizer to learn the best parameters to pass to that circuit to tell it how much to rotate each qubit by. That way it can reduce the energy of this function. That way we can get our result. Okay, so these outputs don't seem, you know, immensely helpful just on their face. Okay, but you know, we get out this energy function for our x. Okay, this is labeling the iterations and the cost. Okay, so now that we found our optimal parameters for this QAOA circuit, we can assign these parameters to the circuit, and use a sampler to obtain the final probability distribution of bit string measurements. So we want to know whether we're applying, x1 is in group 0, x2 is in group 1, x3 is in group 0, those things. But what we did is we used our estimator to minimize the energy of the function, to minimize that inverse of maximizing the number of edges we cut. We just made that negative. And so now that we have found these parameters, we can now use a sampler to get the exact bit string for which group each node has been placed into. Okay, so I assign the parameters that we found from our result. Okay, it's pretty much the same circuit. And now I run that same circuit through a sampler. That way I can actually get those measurements from the circuit. I'm going to run it for 10,000 shots. I'm applying these error mitigation techniques just like before. I have a pub that is just my optimized circuit. I don't need to pass any parameters or anything because that's already included whenever I set this up here. All right, and so I make my measurement. I run this job. Okay, I have my counts integers and my counts binary. And then I have my final distributions. So let's turn this into a more readable format. So I'm just going to make a function to read out from my quantum circuit, and the resulting bit string I get out is this 01101. So, node 2, 3, and 5 are placed into one group, and nodes 1 and 4 are placed into another group. This is what the output of my final distribution looks like. Okay, you can see it's still a little bit noisy, but what we're saying here is there's more than one best cut. Or not necessarily more than one best cut, but there's more than one good cut here. We're ranking the energy of how well this satisfies that place the nodes in two groups that maximizes the number of edges cut. And we can see here that we have grouped that these nodes should be in one group and these nodes should be in another. All right, and we can calculate the value of this cut as cutting 5 edges, which is ideal, just as the problem was formulated here. Now, I've said this is something that's pretty easy to sit down and do on pen and paper, but even if you go to a graph that has twice this number of nodes, that has 10 edges, it becomes less and less trivial as the number of edges increases. This grouping things into groups 0 and 1 such that you maximize a function is incredibly important in a lot of domains. This is selecting a subset out of a high number of permutations, often a factorial number of permutations. That way you can, maximize some type of value, whether that's selecting stocks in a financial portfolio. That could be routing, equipment, just anything you can think of where you have to take a look at a vast number of possibilities and try to determine which group should we include and which group should we exclude. That knapsack problem where, hey, we have limited resources on what things cost that we can buy, and we have to calculate what their value is and how do we fit that best in. So that's my presentation on QAOA. Does anybody have some questions? I know this is a little bit fast, and it will take time to sort through it to fully understand how that cost Hamiltonian works, or that mixer Hamiltonian works. But I think you should be able to see that a efficient way to select from 10 factorial, 20 factorial choices, you can see the value that can have as far as optimizing whatever you're doing. All right. I don't think I'm seeing any questions. Thank you everyone for coming out. At 1 o'clock, Dr. Yuji Lee will be talking about quantum computing in robotics and how necessary that is, from everything from robotic pathfinding to allocating tasks to groups of robots. She's done lots of work of trying to take a look at these difficult problems in robotics. Robotics, as far as it's come, is still very nascent on what it does, and much of that is due to trying to solve these hard combinatorial problems efficiently. And so Dr. Lee will be talking about that. Please come and join us for that. And then this afternoon, I'll be going deeper into variational quantum circuits and hybrid workflows, where you have a classical portion of your algorithm and a quantum portion of your algorithm and how you make them play together. Thank you very much, everyone.